Hello, everyone. My name is Eric Letter, and I'm doing this video as an additional file to my master thesis on my title right now for it, as you can see here, is kind of the optimization of a functionally graded fracture fixation plate, prevent the bone fracturing at an edge of the plate. And the best illustration for my thesis is this picture, which I got from a surgeon at the center in Utrecht, University Medical Center. What you can see here is that there was a patient with a fracture fixation plate that was used initially to help the bone heal, given a fracture somewhere here in the bone. And what happened is that there was a refracture, there was a new fracture here at the edge of the plate, which you can see close to this last screw, right? So that seems to happen a lot with patients who have a fracture fixation plate. There's this fracture at the edge of the plate, and my professor posed this problem to me. He told me about it and proposed it to me as a master thesis project, and I've been working on it since. His hypothesis, to be more precise, is as follows. Okay, so here's the report. I'm not going to go through everything. I just want to summarize the work I've done in this thesis in a relatively short video, I hope. Okay, so here's a better picture of some of the patients to whom this happens, which are children with osteogenesis imperfecta. The surgeon who gave me the pictures, he deals with these patients, so I'm using them as an example. But this phenomenon, this refracture, could happen to anyone who has a fracture fixation plate. Okay, so here is a picture that illustrates better the hypothesis that my professor thought about. So as you can see, well, there is a fracture at the edge of the plate, and that is because we hypothesize that's because there is an increase in stress. There are these big stresses, and that has actually been demonstrated before. So yeah, there are these big stresses at the edge of the plate, and we want to reduce them in order for the bone not to fracture. Here you can see the type of loading. These are two moments at the edges that we are assuming for the bone, which is realistic, as this is what happens when a bone is loaded. Anyway, so in order to reduce them, we hypothesize that if you change the distribution of Young's modulus along the plate, so here it's just sectioning it. You don't have to section it; can be a continuous distribution, but just let's say we would section it and change the Young's modulus at different locations. So basically, the question that we're trying to answer is what? Well, first of all, the first hypothesis is that the Young's modulus is actually the most influential factor, or is a very influential factor in reducing these peak stresses. And then we think that by finding the distribution, so what distribution of Young's modulus would give us the lowest peaks? However, this is not the whole thing. This is not the end, because okay, so let's say that we find that by reducing the Young's modulus of the whole plate to something very low, like let's make this plastic, right? Let's make the plate plastic, and then we see that the peaks are in fact reduced like these a lot, and the bone won't fracture in that sense. But what then happens is that if the plate is very flexible, then there is actually normally like before. This is an image of what happens after the bone has healed, without the screws, by the way. I omitted the screws in this image, but in my whole study I do use screws. Yeah, so normally before this stage there is a fracture, and I have some pictures here showing that earlier. This is better. So there is normally this fracture here in the middle, and there are the screws, right? And what happens when this plate is too too flexible, so like plastic, for example, and then it will deform too much, and this fracture gap, there will be too much movement inside here, and the bone won't be able to heal. This has been demonstrated before. The fracture gap, it needs to move a little bit. There needs to be a little bit of movement, but like enough for healing to take place. But if it's too much, it won't take place. There's a lot of studies, and I discussed them in the introduction. The background is a lot about this, about how fracture fixation plates have been designed to solve this problem, to basically adapt the movement, the interfragmentary movement it's called here, or interfragmentary strain, which is what I deal with in my thesis, so that there is good healing, but not too much, so that then it won't heal. And at the same time, of course, we want to reduce the peak stresses, which is what I discussed before, right? So there is that restriction, that's a constraint to this optimization problem. Constraint is that there has to be enough movement in the fracture gap when there is a fracture. Okay, so the way that I decided to solve this problem was using a finite element model. And here I explain briefly what my overall strategy is. I first want to come up with a suitable geometry, simplified, and for the simplifications I used some justifications. Then I made a finite element model, which I will describe a little bit, and then I went on to the optimization. I did not print or test the implant. Unfortunately, I didn't have the time to do that, but that's something that of course needs to be done if this is ever going to become more than a concept. This is a little bit more about more in depth about what the overall strategy would look like for a really good study. If this is ever going to become a real thing, then I believe the bone has to, the bone geometry has to be more realistic, and for that it has to be scanned from real bone, and then also the plate can be derived from that, some parameters of that scan. Some researchers have come up with methods to do that directly with some parameters of the bone. You create an initial plate. So this could be done patient specific, right? So for every patient that needs an implant, this could be done, and then the model, and then eventually the plate could be printed for that person in a quick manner, right? Okay, these are the steps of the finite element model. Usually you measured contact, but I'm going to go through that more in my a little bit later. Okay, so here's first part is really the finite element model creation. So when I'm going to make my finite element model, so I start with the geometry. Let me just, I'm going to go to Abaqus to show you that. I think I can show that better here. Okay, so I did this in Abaqus, as you can see, and here is, so I started, here's the model true, which I like because then I can go step by step. So first I modeled the bone, which you can see I modeled it as a perfect tube with the cortical thickness of 4 millimeters, some screws of, I believe it's something about 4 millimeters diameter, and I took these dimensions from some reference implant and also bone that the surgeon gave to me. And I made it bicortical. As you can see, sometimes plates are made only one side has holes, but it has been proven that it works better if it's bicortical, right? Okay, and then the plate. Well, this one here is already sectioned, but ignore that for now. So as you can see here, there are 4 screws in either side. I do a parametric study where I investigate what would happen if you change that, and if you change the thickness of the plate. But it was in the implant that the surgeon used 4 screws in either side, and I also saw in a review that this is the preferred, these or 3 on either side. 3 on either side are the minimum allowed number of screws. Okay, so by the way, you probably noticed that this is without a fracture, right? Okay, so this is the assembly, yeah, of the geometry. I'll explain this sectioning. Okay, so then, as you all know, I applied materials. So the different materials were bone material, which I chose to be 15 gigapascals. I put it here as 15,000 megapascals with a Poisson ratio of 0.3. Made it isotropic because as in my literature study, I actually analyzed, I reviewed 21 papers of studies with finite element modeling of fracture fixation, and I found that most of them use isotropic, and the accuracy. Also, one of my criteria for these articles that I reviewed was that they were validated, so that I could see what accuracy they had. And what I found is that they, like most of them, use isotropic material, homogeneous as well, and this worked accurately. And I discussed that more thoroughly at the discussion of my thesis and also in the literature review. Yeah, so basically, just because it's isotropic, only one Young's modulus needed, and it's assumed that it's in all directions the same. Yeah. And for, I have 2 sections here, but actually, in this case, the whole implant is made of the same material, which I made it here 110,000 110 gigapascals, which is what I found to be the Young's modulus of titanium. And the Poisson ratio is 0.3. I put 0.301 here, but that's to help me in the optimization process, because I read these files from MATLAB. Okay, so yeah, there was the material, right? So in order for the mesh, you will see. Let me just show you the mesh. So as you can see, I think the mesh is quite good for example, the contacts that I will set. You can see that this here is right in line with the bone and the screw are the same, and that speeds up things. I found that speeds it up if they are well aligned, and that's why I didn't want to use tetrahedral elements. Also, there were more elements for the same volume, I found. And in general, I got better results by using these. These was not easy to achieve, though. I had to do all this. You can see all this sectioning and trial and error. I tried a lot of things. I didn't find people who had already done this, so I sectioned it like that, and also like this. And then I also had to create some sections for the screws. You can see that the screws are also quite nicely meshed, right? Yeah. So yeah, and so on. I did a lot of sectioning in order to measure like that. Okay, the next thing I guess to discuss are the contacts. So one of the contacts was, as you can see, between the bones, the screws, and the surrounding bone around it, right? And as some of you might know, there's a lot of options in this program, such as Abaqus, for the contact modeling. And I went to the guide and I looked at each of these options, and I developed some understanding for them. And one of the things I concluded is that you can use small sliding. They do already a sort of study in the Abaqus guide that shows that using small sliding does not affect the result, the accuracy of the results much at all. And so I used that already from the beginning. The master and slave surface, well, the master surface should be the most rigid body, and the slave surface the less rigid body. So the screws were the master surface in this case. These I discuss it more in my report as well, and I do in a parametric study. I compare different contacts. I do a parametric study to compare different contact types, especially these and the node to surface. Surface to surface, I found in the Abaqus guide, is to do with, so instead of relating the nodes of the implant and the bone and calculating the contact stresses based on those two, or the contact distance, sorry, it does it using points in between different nodes of the slave surface, and it relates those with the closest node of the master surface. So it doesn't use the nodes themselves, but points that are in between the nodes. So that's good for when the mesh is not very accurate. But in my case, the mesh is quite accurate, so I can use either. And I found it didn't. And then I found that this was actually faster, right? So I stuck with this. And for others, I also read in the guide, but I don't describe it too much. And more exact, the interaction property I used here is frictionless, but there's a reason why I decided to do frictionless. But here I also compared it to using a friction coefficient of 0.2, and that you can find a comparison of the results in my report. Okay. Well, normally there will also be you can see, by the way, that I didn't. There's a gap between the bone and the implant of 1 millimeter, and I did this because that's what's usually done nowadays with the locking screw mechanism. The screw is locked into the plate, so it doesn't have to be press tied onto the bone, and it's already locked in there. And there's a part of my report where I explain why this is much better, as it allows for the load to come from. Yeah, I explained this thoroughly in my report, so one can refer to that. Okay, but so here I actually have the contact. You could model the contact between the bone and the screw and the plate, but I made a study in which I showed that there is only a little bit of contact with the moment that I use. By the way, the moment that I use, there's two moments at the sides of the bone, and each of them are of 60 Newton meters. All right. Yeah, and 60 on the other side. As you can see here, this arrow shows it, and there's an explanation for why it shows those values in the report as well. And it goes in this direction around the x-axis in each of the sides, such that I'll show you later the deformation of the bone, and this makes it more intuitive what the loading was. But yeah, it's just two moments around the x-axis in either side here. This one's positive, this one's negative. Okay. Yeah, so normally you could model the contact between the bone and the plate, but I found the deformation was not very much, so there's barely any contact. And then I did a study and compared the stress distribution, and the stress peaks, which is the maximum stress, which is what we're interested in, doesn't seem to change much, and it takes longer with the contact. So I chose to just suppress it like this, right? Okay, so that's it for and this is one of the reasons why I wanted to do this video, because I think this kind of thing showing in a presentation or in the report is difficult. I also did a tide model. At the beginning, I actually didn't work with screws. I worked only with a tide model, so I present here also how that was done. And I can show you this here too. It's this one. It's just the plate is tied to the bone, At first I was a bit this is something my supervisor suggested to start with, and at first I was a bit confused by it, but in fact you get a very similar stress distribution, especially relating to these peaks at the edges of the plate. And it's nice to see, because then you already know that it's not really the screws what is causing the stress peaks as such. Okay, so, and then there's the model of the screws. I already explained it. Oh, then there is of course one more with a fracture gap. And that one I can show it here. Well, I didn't actually model a fracture gap. I mean, I did. It was, but I just did it as a piece of material in the middle that happens to have a very low Young's modulus of 10 megapascals. See this section here. I made it into fracture of, I called it a fracture, and it's 10 megapascals, right? So it's almost negligible, and then I can calculate the strain in there, which I take as the interfragmentary strain. Yeah. Okay. Go back to my report. So material properties, I discuss here why I chose each property, all the values, the physiological loading and boundary conditions. I explain here the loading, as I showed you earlier, these 2 moments here of 60 Newton meters. The contact properties, I did this parametric study I talked about before. And then for the mesh, I also did a mesh, not quite the typical mesh refinement study, but I did a study to find what was the best model to use that would satisfy all my needs for this study, for this project. So the result of the contact stress analysis is shown here. This is the contact pressure, which is one of the 3 components of the contact, one of the 3 normal components of the contact stress tensor. And so what you can see is that in light red is, no, in dark red is the control case, which had so it had surface to surface contact from the all the choices I showed earlier. If you go back in the video to all the choices that were there, those were the control. Apart from the frictionless, the control had 0.2 friction coefficient. Okay, and I did a few extra cases to compare. So if you do a frictionless, the peaks increase somewhat. If you use a node to surface, it barely changes. As you can see, it decreases a little bit. If you use a plate contact, this is the interesting one. You can see that the peak is actually, maximum stress is actually almost the same. You can see the green somewhere here. So that doesn't really affect the maximum stress too much. If you use tied, so if you tie the screws instead of using actual contact, is this orange one here, which is clearly nothing like the real distribution, and the peaks are very low. So I didn't use that. And then in light blue here, very light blue, is the tied, the whole plate tied to the bone, like like I showed you, right? And you can see that there are some peaks here at the plate, but they're very much lower. But then I did an extra analysis to see why they're so low, and well, they're so much lower, and you can see them. A lot of it comes from the holes, actually. There's some peaks, stresses only because of the holes. And that's the main difference between the case of only tight plate and then having the screws and holes. Okay, but then I also measured the time it took for each of the simulations, and I found out that the frictionless case reduces the time it takes by a lot. It's now 38 seconds. It reduced it by almost believe no, it's 25%, right? And that's very favorable because I'm planning to do an optimization. I was planning to do an optimization at the end, so I decided to use this one because also the peak stresses the distribution was very similar and the peak stresses are actually increased, and we want to minimize them. So it's still very good, and I can use that. Okay, the next thing was here's plotting for the simulation time. The next thing was the mesh study. So I used different measures, but actually my objective here was again to find the minimum time for a case that was reasonable. So if so the lowest number of elements allowed, basically. And my criteria was that the maximum stress was similar to the or that the stress distribution was similar to the real case. But okay, so I'll just show you the results. So these were the results I found using the von Mises stress here in this axis. And so red is the most accurate, the most elements, 16,000 elements in total. And blue here is 3,000 elements, the lowest elements I tried. And well, you can see that the peak stress, the maximum stress did increase somewhat, but it increased. And as I said earlier as well, I'm interested in minimizing these peak stresses. So it's the real value of this peak is not so important to me. I just want to know what makes this decrease, right, to its minimum level. What the real value is that will be important later for a validation study, for instance. But in here, that wasn't too important to me. So I used this blue curve. And I didn't care too much about these peaks here. So that's also why. Here I plot this one here in orange is this computation time. And you can see that with 3,000 elements, it takes a lot less time. It's a lot faster. So that's also why I want to use that. And here, just in the blue, I show that also as you decrease the number of elements, the maximum stress increases. But if you look at it in distribution, you can see that this is not really as significant because of the reasons I just explained. And the contact pressure helps me even more with this argument. You can see that it's almost the same for all of them. And to show you how much difference there actually is between these, I have this here. Yeah, so this one was the case, the normal case, right? So with 16,000 elements in total. And then with 3,000 elements, this is the one. It's this one, and it seems like it's not enough. But as you can see, that I showed the results are reasonable, and it's good. It is good enough. And I measured these sections here a little bit better because I do think that influences. That's where the contact takes place, or the peaks are there. So I refined that a little bit with some sectioning. Okay, so next I did a parametric study, as I mentioned in the beginning of the video, to show what the influence of certain parameters is, and mainly not the main goal of doing this parametric study, and the reason why I did a whole section for it in my thesis report, is that I want to answer this question: is the material the most influential parameter to the implant's performance? because I'm only using, my hypothesis was that by reducing the material, and then also the first part of the hypothesis is that the material is the most influential parameter. So is it the most influential parameter? Someone else did a study in which they did a parametric study by using the Taguchi method, where instead of taking all the possible combinations of different material properties, he takes only some of them as they are statistically all that is needed, according to Taguchi. He, in this other study, they used the material, the thickness, some inserts, and an angle, so an oblique screw of 45 degrees. And he basically found out that the objective function was the maximum stress in the plate, actually. So they found out that the material has 60% influence in the maximum stress in the risk of failure of the plate. But this is for the plate, and as I said before, I am doing my study for the risk of failure of the bone. All right. Okay, so I also investigated 4 parameters, very similar to what he did, which were the material, the thickness, the number of screws, and the fillet radius. And to show, so as I said, Taguchi, normally between each parameter, I set 3 levels for each parameter, and normally the number of possible combinations between all these parameters is 81. But Taguchi, in the Taguchi method, he explains that you can use only 9 of these combinations that are the most statistically significant, and he says exactly which ones according to the levels you assign, but it doesn't really matter which levels you assign as long as they're all different. Yeah, so these were the 9 statistically most significant in my case. And you can see here, so here I added a fillet, here the thickness is increased, but of course here there's 2 screws, 3 screws, 4 screws, and so on. And yeah, they're all different kinds of combinations. And based on that study, I found that the material, the thickness is actually the most influential parameter for the risk of failure. So the maximum stress seen in the bone. Yeah, which is close to the material is close, but it's apparently not. So here, this answers my question, and it's a no in this case. The material is not the most influential according to this study, the way I did it, right? And then I also did calculate the influence in the interfragmentary strain, which is the parameter that I'm using for healing, for how well the bone heals. And here actually I explain a little bit of what I take there. So for the healing, for the interfragmentary strain, I use the interfragmentary strain in this section. And since it's highest here, the magnitude is actually highest down here. I take the lowest, then an element here. Yeah, so I calculated them all. By the way, these percentages I found here were true in an ANOVA study that uses not the maximum stress and the maximum interfragmentary strain found, but the signal to noise ratio of those values according to this equation. Okay, you can see that better going through the report. Okay, so further, I was interested in the difference between these two. So clearly the material and the thickness are the most influential, and according to this study, the thickness is the most influential. So I wanted to see how big that difference really was. So I did another study in which I decreased, so starting here, the plate thickness is 4 millimeters, and the Young's modulus is 110 gigapascals. Then I reduced it by the percentage of each to 80%, 60, 40. Well, actually, these are not the values I used, but yeah. And to see what happens, and keeping everything else constant. So the way a normal parametric study is really done. And you can see that the difference in the relationship that they have to the maximum von Mises stress is very similar. So yeah, I mean, in the future, I think it's nice if the thickness can also be adapted, optimized. But I didn't do this. And here is the same using the distributions. You can see and understand this one better if you go through my report. Basically, in squares are the material, and in triangles are the thickness. It also shows that there's barely any difference in reducing the by percentage. Right? Okay, here, so I go farther with the material. Before I went only somewhere here, and now I'm going even lower with the material to see what happens to the maximum from easy stress, and it keeps lowering the maximum from easy stress. But I also plotted the maximum interfragmentary strain. So as I said earlier, the higher this interfragmentary strain is, well, if it's too high, it won't heal. And you can see, what is this? Okay, I definitely have to change this too. The maximum information stress is here, and the interfragmentary strain is here. I'll change those two. But basically, yes. So the interfragmentary strain raises, and in my criterion is 1.093 actually. And so if it goes above that, it won't heal well. So you can see already that somewhere along here, if it's already too high, the interfragmentary strain, so the bone won't heal properly. And this goes out to 3 gigapascals, by the way. It looks as if it was 0, but it's 3 gigapascals. Okay. So yeah, here's again to show what happens actually when you reduce the Young's modulus. And yeah, so the peaks are reduced. You can see already by 3 gigapascals, this purple one here, the peak is much lower. And by green, this light green, well, it's already really, really low. But 3 gigapascals is what I assume in my report that is the minimum I can go to because that's what I found to be the Young's modulus of porous titanium, or very porous titanium. So yeah, this is the interfragmentary strain. This is how it looks along if you go around this interfragmentary gap that I created. And yeah, so this is basically from 0 to 360 degrees, or if you look at the circumference, from 0 to almost 100 millimeters. Okay, so next was the optimization, right? So in order to tackle the optimization, I realized there were four main questions I had to address. So first of all, what would be the best objective function to minimize? Second, what constraints can we apply to ensure that the bone heals appropriately during the period when there is a fracture gap? So you have the constraint, and then how can we control the Young's modulus distribution in the implant? And then lastly, how can we actually optimize the distribution? So to answer the first question, I plotted all the possible stress in the bone to compare them, and well, it also showed this formula here to show that the von Mises stress takes into account the normal stress in the x direction, normal stress in the y direction, normal stress, and also the shear stresses. So it's a good way of taking everything into account. And but you can see actually that, so if you look at this stress here, this S33, that's the normal stress in the z direction, the magnitude of that is almost the same as the magnitude of the von Mises stress, which is this green one. So one could also use that actually, but yeah, but I prefer to use this one because it takes everything else into account as well. Then there is also the contact pressure, which actually the reason there's peak stresses is because of the contact pressure. So one could also minimize that, right? But I chose to minimize the von Mises stress. So by minimize I mean minimize the peak, right? So this difference between this here and that. So yeah, it should never really go below 20. Well, kind of a little bit, but then there's a peak stress in the compressive direction. Right? Okay, so I chose the von Mises stress for this reason. The maximum von Mises stress is to be minimized. There's a lot of other options you can use as well, like energy criterion, but I'm using this for now. Okay, so what constraints can we apply to ensure that the bone heals appropriately during the period? There's been a lot of studies, especially by this man Lutz Kleiss, where they discuss what determines appropriate healing for the fracture gap. And in one of the studies, they derived this graph here, where they say that if the interfragmentary strain is below 5%, the magnitude, so either if it's compressive or not, that's another, yeah. So the magnitude has to be below 5% for it to be intermembranous healing, so direct healing, which is what we want. And then there's overall criteria about hydrostatic pressure, but in a later study they say that this side here doesn't really matter because so the stress and the pressure and the strain are related to each other, so one could just use the strain, which is what I did. And also another alternative is using the stiffness of the plate. You can read about this more here, but I still chose the strain as I can get that directly from that element, and it has proven to give good results. It has been proven to give results. Here is more clear the element I use. It's down here. Okay, so then the next thing was how to control the Young's modulus distribution around the implant. So I explained first that the most accurate way would be by changing the Young's modulus of each of the elements, making this plate, first of all, very with a lot of elements, and changing then each element. However, and yeah, these curves are just to show that, of course, the more elements you have, the smoother the distribution could become, right? Yeah. Then here I show that even if I was to only section the plate into 15 possible sections, into 15 sections, sorry, and you can change each of them in 10 possible levels of Young's modulus. That would create a, and then the other side is also 15, but I mirror everything, all the properties. So that would create a 15-dimensional problem of 10 to the 15 possible combinations, and that would take my computer about 10 to the 8 years of computations, to complete. So that's not feasible in that way. Well, if this is all because I'm making the space discrete, right? Of course, an optimization routine wouldn't go through all those possible combinations, right? So with a good optimization technique, you could divide the plate into a lot of different sections. But to start with, to make the problem a little bit simpler to begin with, I section the plate into less. I start with actually just 3 sections. So these are the 3 of them, and it's actually only 2 parameters because I keep so this is 1, and then the outer edges. So the edges material and the inner material are the 2 parameters, and even just these 2 parameters, there's already a 10 to 100 combinations I had to run. And for these, I did this in MATLAB, and let me show you. I did it here in MATLAB, and So first of all, let's go to the maximum stress. So I calculated for all those 100 combinations, the maximum stress in each of them. So to see here is in these two axes are the Young's modulus. Here is the outer edges Young's modulus, and then here is the inner edges Young's modulus. And so what you can see first of all is that by changing the Young's modulus of the outer edges, clearly the maximum stress is affected a lot more. It's reduced very greatly, and reducing the inner material is not really as influential. I mean, if you keep the inner material at 120 and you reduce the outer edges to a better way to show this, I have this here, is like this, right? So at this point where the inner material is 110 and the outer edges is lower, you get a very low maximum. This is, so this is actually the maximum stress, right? And you get a very low maximum stress if the edges are low. However, if you have this one at 110 and this at its lowest point, you get this here, which is not as low. So the edges are more influential. That's what we find here for the maximum stress. And then for the maximum interfragmentary strain, first show it like this. See that both the inner and the outer material have a similar influence, right? And then if we go and plot it like this, we see so yeah, the lower the material Young's modulus is, the higher the interfragmentary strain, the more movement. That's what we expect. But the inner material is actually more influential. Yeah, which you can also see better in my report. But anyway, these are some. Even though it's a simple case, I found it to be a very nice, right? And then what I did was that, okay, so if you look again at this, I closed it. If you look again at this graph, so some of these sections, wherever it's higher than 1.093%, I defined it that it would be too high. The interfragmentary strain would be too high for appropriate healing. And so I did a criterion like that in MATLAB, and what I found was the following. So this is the maximum stress, actually, but the red areas is where the interfragmentary strain is too high to heal. So this is a constrained allowed space. So that's how a constraint optimization would do it. Of course, usually the space is much larger, and then so the optimum is found to be here, right? You can see clearly at a outer edges material very low, of 3 gigapascals actually, and inner edges of around 75 gigapascals. So this is That's the result of that optimization process. And I rectify it by running both models in Abaqus and plotting the distribution. In red is the initial with 110 gigapascals, and in green is the reduced with the optimized case. All right. I do a few more things just to show again that influence of the outer edges and compare it to the influence of the inner edges, to show that the influence of the outer edges is much larger for the maximum stress, and so on. And then I do a 4D investigation. I call it as such because I'm trying to find out which of these, what's the influence of each of these 4 sections in the maximum interferometric strain. And for that, normally I would have to run again 81 combinations. But I use once again this Taguchi method. Each section has only 3 possible levels: 3 gigapascals, 55 gigapascals, or 110 gigapascals. And then that gives me 9 statistically most significant simulations. I run them all, and I find that, as expected, the outermost section has the most influence in reducing the maximum the maximum von Mises stress in the bone. So much more than all the rest. In terms of what reduces the what increases the interferometry strain the most, actually this section appeared to have that, but only by a little bit. It's very well distributed, so I don't make really any conclusions about that. And then I go on to 10-dimensional optimization. To explain this better, I go on here. So if I were to run so in 10 dimensions, what I mean is I section the plate like this. So there's 10 sections in either side. It's mirrored, right? So, and if I would vary each of them, so there are about almost 10 million possible combinations for those 10 sections, right? So this is how it varies if I would start in the sector, start at 3 gigapascals, and I give each of them, oh, by the way, they each have 10 possible values, which is why there are 9 million possible combinations. Sorry, they each have 5 possible values. Otherwise, MATLAB wouldn't be able to handle such a big matrix. And yes, so this is how it normally would increase. But of course, that's not the smart way to do it. And I developed a constraint. I can explain the constraint better here. So you can see some of these simulations have a higher outer edges Young's modulus than the inside. Like, for example, this is higher than here, right? So, but in my study, in the 4D study, and also in the 2D optimization, I found that decreasing the Young's modulus at the outer edges and keeping the inner higher is always the better way to do it. So I made a constraint that says that the outer material can never be higher than the inner material. And that was very handy because number of combinations to only 1001 actually. And this is, in fact, the combinations that are possible. You can see none of these have a higher outer edges Young's modulus than inner, right? And these are only 1000. You can see even already that it's going much faster, right? So I used these 1000 instead. There's still 1000. Okay, so then so there still has to be an optimization. I have to find the optimal within those 1000. And that would take 20 hours if I ran them all, which is doable, but I want to do an optimization also because later on there might be more sections So I want to carry an optimization. But the nice thing about having only 10 sections as opposed to many more for now is that I can actually run those all these combinations in 20 hours and find and check that the optimizer is doing the right thing. So for the optimization, most the common thing to do is to use the gradient-based optimization, such as in a paper written by Rick Husks and R. Böckling, in which they optimized the geometry of a hip implant. So hip prosthesis. But this, what I found is that mostly for continuous, when the space is considered to be continuous in a range, this method is most suitable. But given that the problem I'm considering right now is a discrete problem, I opted for this other option, which is a genetic algorithm, and it uses a similar process than natural selection. It selects the best options from a given set at first by using the fitness function, and it does this selection through selection, crossover, and mutation. And this is all better explained in the MATLAB guide. And I used actually just the MATLAB optimizer for this genetic algorithm. And what it did, well, it found this to be the optimal distribution. Outer 30 gigapascals and then inner 80 something gigapascals and so on. It's a little bit more smooth than what we saw for the 2D. And then I did this by myself. I ran all the 1001 simulations, and I found the minimum, the constrained minimum myself. Because the other thing we have to remember is I also told the genetic algorithm that there was the constraint of that the maximum interfragmentary strain had to be higher than 1.093%. So I only consider everything that is higher, and that is everything that is found in this region, which is consistent with this region of the maximum for Mises stress plot. And then I plot only that region, and I find the minimum to be, well, actually I didn't do it this way, but I'm showing it like this here, to be this one, and the 74th model, which I then look at and I compare it with the other one, and I find that it's exactly this one. Yes. So that shows that the genetic algorithm is doing the right thing. However, then I went and I compared that optimal solution to the optimal solution of the 2D optimization, and I found that the 2D optimization gives me a lower stress peaks. And this is most probably because I only used five levels for this one, for this optimization process. So each of these sections only had 5 levels, and while as in the 2D, even though it was only 3 sections, each had 10 possible levels, and that caused this one to arrive at a worse optimal. So yeah, in the future, I think this process should be used, but with a lot more intervals. And yeah, well, perhaps it won't be possible to check if it's the right answer, but it should be. Now it's been checked, so if the process is run again, it should be. And the genetic algorithm solved this in about 65 simulations instead of the 1001, so it's pretty good. Yeah, that's the end. Then I go on. I discuss a lot of things, all my results and the parametric study and what other people have done, and a little bit of why these peaks are not only affected by the material but also by the geometry In fact, it's probably more by the geometry. The inertia and the Young's modulus, usually both, the product of them gives the better idea of rigidity. Yeah, so that's it. I've effectively optimized the implant, which is what I wanted, using a distribution of Young's modulus, and I proved that it is possible. In the future, this should be done more thoroughly, with more sections, perhaps a continuous distribution to use a gradient-based method. But I believe I validated the procedure, the process that is proposed. In terms of the patient-specific methods, that also has to be done in a later stage, and 3D printing possible techniques that also has to be analyzed later on. But I did all the other things I proposed and I set out to do. So that's it. And then there is in an appendix, I did a bit more of a parametric study. Okay, that's it. Thank you for listening.